Hello, good afternoon, my dear students. This is again your Virat Kumar, lecturer in Electrical and Electronics Engineering from the same Institute of Government Polytechnic, Vadipalli, with the semester of 4, the subject of AC machines with the code of 18EE403C. And today we are here to discuss about Scott connection and the topic of three-phase transformers. Okay. It's a small recap of previous PPT, a previous session that we have discussed in the last session about need of instrument transformers, current transformer, potential transformer, and precautions while using CT, applications of instrument transformer, and measurement of power in conjunction with CT and PT. These are the things which we have PPTs. And today's objective is, on the completion of this period, you will be able to know about the Scott connection and advantages and disadvantages, and also some applications of Scott connection. So what is actually a Scott connection? What are the advantages of it and disadvantages? And what kind of applications are involved with this Scott connection? Scott connection. TT connection or Scott connection is a connection from which TT connection. It is also, the Scott connection can also be called as TT connection, or Scott connection is a connection from which three-phase to three-phase conversion is obtained, three-phase to two-phase transformation, and two-phase to three-phase transformation. So mainly Scott connection is a connection which is done from three-phase to three-phase conversion is obtained, three-phase to two-phase transformation, and two-phase to three-phase transformation. These can be obtained from Scott connection. Three-phase to three-phase conversion. Scott connection consists of a center tapped 1:1 ratio main transformer and an 86.6% ratio teaser transformer. Scott connection mainly consists of this center tapped 1:1 ratio main transformer and an 86.6% ratio teaser transformer. So here one end of the teaser transformer is joined to the center tap of the main transformer. The current in teaser transformer is in phase with the voltage, and current leads the voltage by 30 degrees in half the portion of main transformer and lags the voltage by 30 degrees in the rest of the winding. Now three-phase to two-phase conversion. This conversion is required to supply two-phase furnaces to link two-phase circuit with three-phase system, and also to supply a three-phase apparatus from a two-phase supply source. This connection requires two transformers which may be identical but having suitable tappings. Three-phase to two-phase conversion. This conversion is required to supply two-phase furnaces to link two-phase circuit with three-phase system, and also to supply a three-phase apparatus from a two-phase supply source. And this connection requires two transformers which may be identical but having suitable taps. So now you can see a three-phase to two-phase conversion circuit diagrams or a connection diagrams, where you can see here from the diagram, this is the main diagram and this is A and B. Three phases, 1, 2 and 3, and there is a tapping over here that is called Scott tap, similarly to this. And to the secondary we are taking two-phase wire. We'll see how it is in the primary and in the secondary. See, this is actually the primary winding whereof about 100 volts. There is one more connection with tapping of A1 AD coil. This is CB coil with the tapping. It can be changed, and this is of about 86.6 volts. And coming to the secondary, so from this 86.6 volts, which is AD, now CB is primary and small cb is secondary, which is of same 100 volts, balanced. Secondaries are balanced, and from this tapping we just obtained 86.6 volts. Capital AD is the primary and small AD is secondary. Then the same diagrams, you can observe that if the secondary of both the transformers have the same number of turns, if the secondary of both the transformers have the same number of turns, then secondary voltage will be equal in magnitude, thus resulting in a symmetrical two-phase three-wire system. Have got the point that if the secondary of both the transformers have the same number of turns, then secondary voltage will be equal in magnitude, thus resulting in a symmetrical two-phase three-wire system. And the same, the number of turns between capital A and B should be also root 3 by 2 into N1 for making volt per turn, the same in both primaries. Then for secondary having equal turns, the secondary terminal voltages will be equal in magnitude, although in phase quadrature. He is telling us that the number of turns between capital A and D, this over here in the primary, the number of turns between A and D should be also root 3 by 2 into N1. That should be for making volt per turn, the same in both primaries. So then for secondary having equal turns, the secondary terminal voltages will be equal in magnitude, although in phase quadrature. So moving on to the next slide, three-phase to two-phase conversion. You can see from three-phase we can convert into two-phase in this way that you can see the diagram of here, three phases. The first one is it's center tapped with this n1 by 2 and n1 by 2, and this is root 3 by 2 n1, and here n2 with the load. This is also an n2 with the load. So here you can see the current I1M, I1M and I1M from all these three phases, whereas the CB coil is split into two, that is denoted by N1 by 2 and N1 by 2, and at the center there is a tapping of AD coil, which is of root 3 by 2 N1. The number of turns are root 3 by 2 N1, and thereby N2 is connected to the load with a current of I2T. And there is also another coil of N2 in the below, the bottom, connected to the load with a current of I2M, where T is teaser transformer and M is main transformer. As I've said in the previous slides, that it just requires a main transformer and a teaser transformer. This is it. I2T is the current of teaser transformer, and this is I2M. This is the current of main transformer. And by observing the primaries and secondaries, see the CB coil is split into into two, so that is the voltage also splits into two, V by 2 and V by 2, and there is a center tapped coil AD, which is having the turns ratio of root 3 by 2 N1. In turn, if we just call it as N, then it is 2 by 3 divided 1 by 3. So from this joining AC we get the voltage, AB we get the voltage, and CB is also the voltage total V, and CD has V by 2 and DB has V by 2. This is the primary side. Whereas coming to the secondary, this voltage V2T, teaser transformer voltage and the teaser transformer current are in phase, and the main transformer voltage and the main transformer current are in phase, and again both these are in with a phase difference of 90 degrees, and both these are connected in a phase difference of 90 degrees electrical. Two phase to three phase cord connection transformer used at Niagara waterfalls in the year of 1895. Two phase to three phase cord connection transformer used at Niagara waterfalls in the year of 1895. You can see the pictures. Which are used in the Niagara waterfalls in the United States of America. Now we'll move on to the advantages of Scott connection. The Scott connection evenly distributes a balanced load between the phases of the source. The transformer can deliver 92.8% of the capacity, and there is a cost saving due to the two coil T connection in lieu of the traditional 3-coil primary to 3-coil secondary transformer. And with the help of two transformers, three-phase supply can be maintained. Coming to the disadvantages of Scott connection, the full rating of the transformer is not utilized. That is, the full rating of the transformers is not utilized. Now the teaser transformer operates at only 0.866 of its rated voltage. So these are the main advantages of Scott connection, that the full rating of the transformers is not utilized, and the teaser transformer operates at only 0.866 of its rated voltage, that is 86.6% of its rated voltage. So that is about the Scott connection. Let us see a summary of this session. So in this class we have learnt about Scott connections in use to get 3-phase to 2-phase supply and vice versa, that is from 2-phase to 3-phase, and 3-phase to 3-phase supply using 2 transformers, and advantages and disadvantages. These are the things which we have seen in this session. So let us see a small quiz in it. For obtaining Scott connection, the main transformer should have a tap of dash percent of the windings. Let us think for a while and just guess the answer correctly. For obtaining Scott connection, the main transformer should have a tap of 25% or 50% or 86.6% or 58% of the winding. I hope it is 86.6%. Let us see. I think this is for teaser transformer, but whereas for main transformer, okay, for main transformers we have divided that winding into 2, right? So it is 50% of the winding. For teaser transformer it is 86.6. That may be in the next question, I think. So for obtaining Scott connection, the main transformer should have a tap of 50% of the winding. Scott connection transformer facilitates conversion of 3-phase to single phase? No. Conversion of 2-phase to single phase? No. Conversion of star to delta? No. Conversion of 3-phase to 2-phase and vice versa. Okay, this may be right. 3-phase to 2-phase and from 2-phase to 3-phase also, vice versa. So this is double right. So you can see. So Scott connection transformer facilitates conversion of 3-phase to 2-phase. So there are some frequently asked questions in this topic, like explain Scott connection for conversion from 3-phase to 3-phase with neat sketch, and explain Scott connection for converting 3-phase to 2-phase with a neat sketch, and state the applications of Scott connection, and state the advantages and disadvantages of Scott connection. So these are some frequently asked questions. Thank you. I hope you have got some idea on SCART connection. Thank you one and all.